Alright, good morning. So what I'm going to do today for this tutorial is we're going to attempt this question again, which I've done on week 10 Friday's lecture before everything go online. I'll solve this problem, and because I have a few students asking me question, why can't we use this, or why can't we use the tau shear max to find the radius? Why should we use the yield strength? Okay. But now, what I'd like to do now is I'm going to change this from tension to normal. Okay. So we have a structure, a shaft, and then if we're going to sketch out our transformation, so we have our respective transformation. Oops, wrong side. So we have our respective transformation. So this will be our usual y, our x. Then we come with our z. Okay, so this is our y, x, z. Okay. Then we are going to put our elements. We're going to place our elements. Okay, so where to place our elements, I'm going to repeat this again because I realized some of you were not there in my lecture on Friday. So there are four ways that we can put our elements. Okay, so if we were to view this in the YZ plane, okay, so we were to view this in our YZ plane. Right, so we look at the YZ plane, and then we have our shaft. Okay, so this is our shaft. So we can look at element. Okay, so we're going to have four different positions. Okay, 1, 2, 3, and 4. So this is my element A, element B, element C, and our element D. Okay, and at the center over here, this is our neutral axis. Okay, so that's our neutral axis. So if we were to look at our loading, right, so we know from our loading over here, we know that moment in Z is equal to 1,500 pound-inch or pound-feet. So I highly recommend that we convert to inches, and then we'll want to multiply by 12. So the 12 is because we're going to change it to pound-inch. So 18 times 10 to the power 3 pound-inch. Then we have moment in the, we only have moment in Z, then we have torque in the X direction. It's equal to 2,300 pound-feet. Again, convert to pound-inch. So it's 27,027.6 times 10 to the power 3 pound-inches. Then we have load in the X direction. So this is 2,500 pounds. So if we look at the load distribution, right? So if we look at the shear stress distribution, so the shear stress, all of them, right? So the shear stress, the tau, due to the torque in the X direction, all of them will see the same tau. Okay, so all of them will see the same tau, 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 tau. All of them will see the same taus. Normal stress in the x direction due to px, all of them again will see the same. Px, 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 px. What I'm trying to do down here is to find which is the element that we should be analyzing. Okay, we should be analyzing. And the px will be in negative compression. Negative, negative, sorry, not px. The normal stress, I do apologize. So the normal stress will be negative, negative, due to axial loading, right? So, yep, so this is negative. And finally, the stress in the x direction, right, M due to mz, right? So we look at mz down here, we realize that mz over here at element C will be, the stress x due to the moment will be equal to 0. The stress x at element D due to the moment is equal to 0. The stress x due to the moment will be equal to positive. Okay, so I'm going to put positive down here. And down here, element D, B for Bravo, the stress x due to the moment will be negative. So from this context, where you see that has the highest stress loading is going to be element B. Okay, because yes, both compressive axial loading and due to bending. Whereas this is negative, positive, it will not be as high. No point considering elements C and D because the moment induced 0. Okay, so from here we're going to analyze element B. As I said, I've changed this question because I changed this to what? Normal stress. Okay, so here, right? So element B element B will be exposed to the maximum compressive stress. Okay, so if we view at element B now, okay, so we're going to orientate our element looking at element B. So we're going to view, so we go look at below the shaft, so there is our X. Okay, so we draw transformation. This is our X. This is our Z. So if we look at our loading for element, right? So this is the element. We are looking below the shaft now. So once we are looking below the shaft, we know this is our stress X. We know it's going to see compression. And if you look at the torque will be running in this direction. Torque in the X direction, right? So the element will want to deform this way. So what we have is a negative shear configuration. Okay, so this will be our shear in X, Z. Okay, so X plane or plane intersecting X-axis, Z direction. So from here we know that stress X will be negative. Stress shear XZ is equal to shear ZX will also be negative, and we know that stress in normal stress in the z direction is equal to 0. Okay, so now let's start writing out our equation now. Okay, so now let's look at due to px. Right, so but before we go on, let's look at the condition that so we analyzed the structure already. We want to look at the condition we're given. So we are given that the maximum given that it can have the structure will yield at 100 KSI. And they also give us the yield is equal to 50 times 10 to the power 3 psi. So what I've done when I change the equation, now it becomes plus or minus. So what this actually means is if we were given a mole circle, okay, we are given mole circle. Okay, let's look at the context what this actually means. If we are given mole circle now, right? So this is our mole circle. Okay. We are given our operating bracket now. So this is what this is. We are given our operating bracket. So this is our normal stress, right? So this is our normal stress. This is our shear stress. So if this is our shear in yield, okay, so this is our yield strength. Over here, this is our yield strength. And over here, this is our yield, and this is our negative yield. So we are given an operating bracket. Okay, so our mole circle has to be within this operating bracket. Okay? It has to be in this operating bracket. It cannot go beyond that. The circle cannot go outside this square. Okay, or this operating bracket. So why the region that is shade is a no-go zone. Okay, your circle cannot go beyond there. So this is what it's telling us. So we also realize that it also specify that we have to design the shaft based on the maximum shearing stress criteria. Okay, so if we were to reflect back on Tresca, so this is based on Tresca, right? So Tresca, so this is the lecture that we have given on Thursday. Okay, so if we look at Tresca, I'm trying to go back to the formulas. So Tresca has two conditions, right? So one is where stress is equal to 0, stress B is not equal to 0. You can directly use this formula over here, where stress max is equal to shear max is equal to half normal stress max. If it's not, if you have a positive and a negative, like for this case, you have to apply stress max equal to half, or shear max is equal to half normal stress max minus normal stress mean. Okay, so we have to find our stress state and know where our mole circle is. Okay, it's one of our principal stress equal to 0. Okay. So now knowing that, now we have to find the stresses that are induced by the bending moment, axial load, and shear stress. I'll be back. Okay. Okay, this is part 1 of the lecture or of the tutorial.